again I would like to repeat the fact that in 2 dimensions parallelogram, then rectangle, square, then hexagon, okay, are the 4 basic figures, because centered rectangular lattice, even though the building block is a general say rhombus, it can be accommodated by centering in a rectangle. So, we have seen 4 geometrical figures, say parallelogram, rectangle, square and hexagon. We are going to see that correspondingly in 3 dimensions you have 7 geometrical figures, which I will write here, the 3 dimensional lattices. 1 triclinic, 2 monoclinic, I will explain each of these later, 3 orthorhombic, 4 trigonal, 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 5 tetragonal, 6 hexagonal, okay, 7 cubic. We say these are the 7 crystal systems in 3 dimensions. These are the real geometry of crystalline solids, often called 7 crystal systems. Okay. Now, I will specify the geometry of this, then immediately you can correlate with the geometry of the 2 dimensional lattices, which we have already seen. Shall I do it now? See, I will write here A different from B, different from C, alpha different from beta, different from gamma, different from 90 degrees. I will explain. Okay, I will come to this with renewed vigor a bit later. Okay, this is triclinic, because I have quoted this because its 2-dimensional counterpart you are quite familiar with, oblique lattice, A different from B, alpha not equal to 90. Don't you see that? This is more sophisticated than that thing. Then here I have A different from B, different from C for the monoclinic, alpha equal to beta equal to 90 degrees, not equal to gamma. Okay, I will explain. This is monoclinic. Orthorhombic, A different from B, different from C, alpha equal to beta equal to gamma equal to 90 degrees. In fact, you are quite comfortable here, because this is the rectangular lattice in 2 dimensions reborn in a more sophisticated manner. A different from B, alpha equal to 90 degrees, that is the rectangular lattice which you have seen in 2 dimensions. Now, in 3 dimensions you have A different from B, different from C, alpha equal to beta equal to gamma equal to 90 degrees. So, you will see that triclinic is oblique lattice reborn and orthorhombic lattice is rectangular lattice reborn. Now, again cubic, I will take this up now. Cubic, A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. See, this is thus most symmetric figure. A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees is the most symmetric figure. Now, this is evidently the so called square lattice reborn, because for the square lattice we have already seen A equal to B, alpha equal to 90 degrees. See, so this is certainly very similar to that, but more sophisticated. But there are other 3 more new entrants here which require some more explanation. I will take this up now, tetragonal. I will write A equal to B not equal to C, alpha equal to beta equal to gamma. See, this is something intermediate in symmetry between the orthorhombic and cubic. See, as I told you, orthorhombic is the good old 2-dimensional rectangular lattice reborn in 3-dimensional world, and cubic is square lattice reborn, but tetragonal is a new thing which is intermediate in symmetry between orthorhombic and cubic. This is because as the dimensions increase, more and more possibilities open up, okay, as we are going to see later. So, this is tetragonal is a typical example. Now, hexagonal lattice in 3 dimensions is exactly the 3-dimensional counterpart of hexagonal lattice in 2 dimensions, that is A equal to B not equal to C, alpha equal to say beta equal to 90 degrees, okay, gamma equal to 120 degrees or 120 or 60, that is they are supplementary angles, one can take either. Usually one takes it as 120 degrees. So, hexagonal lattice, I will explain. This is evidently it is 2-dimensional hexagonal lattice reborn in a more sophisticated fashion. The most enigmatic of the lot is trigonal lattice, which requires very detailed explanation. I will first of all quote one more name for it, which is called rhombohedral. Okay, because I will take this up last for explanation because it is very sophisticated. I will write here A equal to B equal to C, alpha equal to beta equal to gamma. Well, I am sure you would be totally confused about this, I am sure, because it is naturally you should be confused because these are really confusing. There are so many pitfalls for you. I will just clear these things a bit later. I will take up these things for discussion, and the trigonal we will encounter as the last of the lot. Okay. Now, so these are the 3-dimensional, see, a very casual perusal of the whole thing will tell you one thing. Shall I put it like this? See, does it not sound like a 2-dimensional journey even though this is actually 3-dimensional? Because if I say oblique, see, that is triclinic is oblique, okay, then orthorhombic is rectangular, cubic is square lattice, then hexagonal lattice is hexagonal in 2 dimensions, and yes, there is no counterpart for this thing in 2 dimensions. Okay, rhombus. Rhombus, we have seen the general rhombus centered rectangular, that is reborn, as we are going to see in this. So, the only thing is, as the dimensions increase from 2 to 3, more and more possibilities open up. You have the situation becomes more fertile for our encountering new and new symmetries. That is what we are going to see. Now, let us take, shall I draw the geometrical figures corresponding to each of these? That will tell you further on the genesis of these things. Let me see, I have written A not equal to B not equal to C, alpha not equal to beta not equal to gamma not equal to 90 degrees. How will such a figure look like? Let me draw it like this. See, Remember, in 2 dimensions, this was the oblique lattice, oblique figure, oblique unit. How will you make it triclinic prism? See, it's something like this. Yes. See, an oblique lattice or an oblique unit cell reborn in with more sophistication in 3 dimensions, I will write here A, B, C. See, A different from B, different from C. See, then this is A, B, C. And the angle opposite to A is alpha, that opposite to B is beta, and that opposite to C is gamma. Alpha not equal to beta, not equal to gamma, not equal to 90. See, this is the most general, say, 3-dimensional repeating unit in 3-dimensional space. You can't have a more general one, because say its every face will be an oblique figure, parallelogram, which we have already encountered. This is a figure which is bounded by so many parallelograms, which you can identify yourself. Okay, so this is the most general building block. Shall I call it oblique prism or triclinic prism? This is often called triclinic prism. We say this is the least symmetric. Now, it will be more profitable if you jump from this triclinic example to the last one cubic example, and which is the cubic building block. Say this is triclinic prism. Cubic prism I will draw here. Yes, A, B, C, alpha, beta, gamma, and I will write here A equal to B. Okay, I have already written it here. A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degrees. Okay, this is called cubic prism. Cubic prism. Okay, it's quite clear that the triclinic prism is the least symmetric among this spectrum of geometrical figures, and the cubic prism is the most symmetric, and the others will be, say, occupying intermediate situations between these two extremes. Shall I now that we are quite sure about what is meant by a triclinic prism, we can try to jump to the next one in the hierarchy, namely monoclinic prism. Okay, because I know you are likely to face some enigma here. How come you have two angles which are simultaneously 90 degrees while one is not 90? Say you are likely to ask the question, shall we not have one of the angles say 90, the others non-90? The answer is a definite no, as we are going to see. Let us see. See, you have in the triclinic situation, I have a typical parallelogram like this. Okay. Yes. See, this angle is evidently, as we have seen, alpha. Okay. Suppose this is made 90. See, suppose this beta, I am going to make this equal to 90. Then what will happen is this vector C A has to go exactly perpendicular to the plane of the board. Then evidently, the moment A goes perpendicular to the plane of the board, say if beta becomes 90, gamma also becomes 90, while alpha not equal to 90. Of course, here say I have written alpha not equal to, I mean in this one, alpha equal to beta equal to 90 and gamma not 90. Okay. That is what I have written here, and certainly it does not clash even though the naming has been changed now, because in this alpha is not equal to 90, okay, beta equal to gamma equal to 90. Okay. Then I think that is explained away. If you want, you can write beta, if you are so keen, beta equal to gamma equal to 90 not equal to alpha, then that exactly corroborates with this one alpha. Okay. The most important point which should be borne in your mind is this: the moment one of the angles is made 90, okay, automatically one more angle becomes 90. There is no question of one of the trio becoming 90 alone. That never happens at all. Okay. Two of them concurrently say become 90. The remaining, the third one can remain non-90. Okay, that's a situation. Say so here. See gamma beta equal to gamma. See now this is like this. This is 90. This is 90. Beta equal to gamma equal to 90, and alpha not equal to 90. This is monoclinic. It is an intermediate situation between orthorhombic and triclinic. There is no such intermediate situation in 2 dimensions, because it is a case of low dimensions. The higher the dimension, as I told you, more possibilities open up. Okay. Now, what about, now let me take this up, tetragonal lattice. See, let us take this as a starting point, orthorhombic, A different from B different from C, alpha equal to beta equal to gamma equal to 90 degrees. That means all the angles are 90 degrees. So, you have a rectangular parallelepiped, okay, as the building block, which is the 3-dimensional counterpart of a regular rectangle. Okay. So, let us start from that, the orthorhombic prism like this. See, rectangles. A, B, C. Then this is 90, 90, 90. This is the orthorhombic prism. This is called, say, shall I write orthorhombic prism. In common parlance, we call it a rectangular parallelepiped, okay, which is the 3-dimensional representative of the regular so called rectangle in 2 dimensions. Now, compare this orthorhombic prism with this cubic prism. Say in cubic prism, all the sides are equal, A, B, C are all equal, cubic prism, A equal to B equal to C. In the orthorhombic prism, A not equal to B, not equal to C, but in both cases all the angles are 90. So, there is so much of angular similarity, okay. The angles are exactly similar in the 2 cases, but the sides are quite dissimilar. Now, suppose I ask you to coin an intermediate case, a hybrid between these 2, what will you do? See, because you can't do you cannot do anything about this angle business because they are already, everything has become 90 degrees, say nothing can be, see there is no difference at all. But here you have A equal to, I mean not equal to B, not equal to C. Here you have A equal to B equal to C. Evidently, it's just commonsensical to say that shall we not have a case where A equal to B not equal to C, that is it maintains part of the personality of this while the remaining part of the personality belongs to this. See, this is typical of this thing, this is typical of this, both are coupled. You take a hybrid of this, that is precisely the tetragonal lattice. See, A different, I mean A equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degrees. This is tetragonal, say, lattice, or the prism is called the tetragonal prism. I will put it, say this is tetragonal prism. Okay. So, this is explained without any difficulty. Tetragonal prism falls into place in this bigger hierarchy. So, we have seen triclinic, monoclinic, orthorhombic, tetragonal and cubic. Only two more things need some explanation, and hexagonal prism, as I told you, there is nothing enigmatic at all. It is just the regular hexagon pushed into 3 dimensions. It is something like a circle becoming a cylinder. Similarly, a regular hexagon becomes a regular hexagonal prism. There is nothing more than that in the case of this. So, I think I need not explain anything with respect to this. It can be presumed to have been explained. Yes, now let us invest some thought, okay, on this more enigmatic trigonal, okay, or rhombohedral, say, lattice. Okay, that requires detailed pondering on geometry. I think I can erase the entire stuff because you have already done, except we are now going to do the so far undone thing, namely trigonal. All the others have been done.